Well, we're fortunate today to have John Larice from the Department of Chemistry at the University of Tennessee to speak to us. I don't have the title of your talk, John, but we'll soon find it out. John got his BS in Wesleyan University and did a postdoc at Penn State University. From 1985 to 2001, he was senior group scientist and group leader at Brookhaven National Laboratory with tenure. I found out from John that unlike Oak Ridge, you get tenure at a certain point. That was kind of interesting. From 2001 to present, he has been professor of chemistry at the University of Tennessee and ORNL, involved with GENS and GIAN, Joint Institute for Neutron Studies and Joint Institute for Advanced Materials. He was a visiting fellow at Cambridge University from 2004 to 2006. He has numerous awards. I won't go through those, but including he's a fellow of the American Association of National Science. His most recent activity is the development of VISION, capital V-I-S-I-O-N, spectrometer at SENS, SNS. The advantage of this technique, this method, this spectrometer, is that because the scattering comes from nuclei, there are no selection rules like you have in infrared or Raman spectroscopy. So the scattering of neutrons off of materials gives you all the vibrations, just has to do with scattering a neutron with a nuclei. So we're going to hear about that today. And so John, thank you very much for coming over.
Well, thank you, Bob, and thank you all for coming today. One of the things that I should say at the beginning is first off, I spent the first 20 years of my career, as you said, at Brookhaven National Lab, and there always was that friendly scientific competition between all of the labs in the U.S., and I always found that to be pretty enjoyable. It was how I first met folks like Ralph Moon and Hal Smith, and interacted with them on some interesting projects that had to do with both inelastic neutron scattering and imaging of neutrons. And I won't tell you about those today. You know, I've been a surface scientist who started off doing NMR at surfaces and then helium atom scattering and then neutrons and X-rays. And I saw that Steve Overberry came today. You have a fine group of surface scientists here. And so much of what I'll tell you about today is a little bit like jumbo shrimp, okay? And that's because neutrons are really a bulk probe, not a surface-sensitive probe, but under certain conditions, especially, and so part of the title where it says nanomaterials, you can actually kind of fake your way into this, and I say that tongue-in-cheekly, by using materials that have large surface-to-volume ratios. And to do some of the spectroscopy that I'm interested in, it's even more of a challenge, because what happens is we've been nanoscientists from the beginning, only the types of systems that we studied were tough because you had to find ones that were really ideal, like many of the ones that Steve and his group worked on, where they were single crystal surfaces. The big challenge, as he knows, was to cross that barrier between ultra-high vacuum, where the pressures were really limited, to real-world problems. Maybe I'm just limited in my ability to understand things, but I wanted to do things in what many of you know as thermodynamic equilibrium. So I wanted to measure catalytic processes that took place at high pressures like they do in real reactors. But I was never allowed to say that because I wasn't supported by the chemical sciences division. I was supported by the material science division. So I could perhaps build catalysts, but I learned the workaround, and my dear old colleague and friend Norman Sutton said, you can't use that word catalysis. So what I used was surface-mediated chemical reactions. Sometimes known as catalysis. So anyway, what I'm going to tell you about today, I've been fortunate, as all of you know, by receiving support from a variety of places, and the University of Tennessee made it possible for me to actually come to the institution, because working with students was one of the edicts, if you like, that I agreed with Ron Thomas that I would do. Try to make this bridge of educating students to use the spallation neutron source. And those of you who know that it's in full operation right now probably don't appreciate the fact that to build an instrument from the ground up, and especially one where you're going to do these things with vibrations and excitations and diffraction, takes about 13 years. And it's a big hunk of your life, but I figured that, it was good enough to do. And I hope some of the examples that I give you say that it was worth it. But you know, in the end, the audience is always the judge. So funding agents are important. Eastman Chemical has been kind to me and my group, and they came to me, and I thought that was that tickled me. There's a picture here of some of the things that the group has done. We have to become masters of thermodynamics, so that when you go to a large facility, you have to be prepared to not waste time. And whether that's a synchrotron X-ray source or a neutron source, you know, people stand in line. And in the early days at the SNS, the calculation was there were so few instruments working that it's a $200 million a year operating budget. It was somewhere around $100,000 per day per instrument, which, wow. Anyway, all of you know about this. If it wasn't for the folks that work with you, you know, what it is that you do is limited by that. And really, if you like some of the things that I tell you about today, it's really the work of these young folks here. And the group has changed just a little bit. The two, if you like, new students, I don't recruit anymore. They just seem to come. And sometimes I get beat over the head for that. But it turns out that in the last 15 months, this guy, Nick Strange, this guy here, Daniele Paraduso, and this young lady, Fatima Wahida, Intel, ST Microelectronics, largest microelectronic manufacturer in Europe, and Stanford University and NREL, they're doing well, and the three of the other folks will finish in the next 18 months. So it's those folks who have done a lot of the work, and it's me who have tried to manage the direction. So if what you hear is what you like, then it's their credit, and if I've taken the wrong direction, blame me. It's always clear that you work with people that are great and keep your interests going in things, and all of you know this since in one way or another you worked here in Oak Ridge. These are some of the people that I've worked with over the year. Postdocs at the beginning. Chuck Sumner at Eastman was really the original touchstone. Stuart Clark has been a longtime friend at Cambridge. Tom Arnold is now going to the European Spallation Source, and I've worked at the Institut Langevin and the ISIS lab as well. Now at Oak Ridge, some of you know some of these folks. Bobby Sumner's still there. Bill Shelton moved to PNNL. Andy Lupini is electron microscopist. Mike Drummond was a postdoc, and so was Eduardo Cruz Silva, better known as Lalo. So what am I going to tell you about? And look, if I get sort of out of line, I think there's one equation, and that's, I think, Bragg's law, but it's at the end. So if I don't get there, it's perfect. And, if you start walking out, I'll know that life is tough. I need to tell you a little bit about why it is that I started down along this line and what it is we did in order to do that. Truth be told, I've been in the chemistry department for a long time, but I'm a physicist and mathematician. And when I first joined the chemistry department at Brookhaven, as I got courted away from physics, my dear friend Marshall Newton at quantum chemistry used to say I was one of them. But he didn't mean one of them. He meant I was one of them down the hill, the physics department. But you know, in time, I really came to appreciate my colleagues in led a materials synthesis group and had some great people. So I'll tell you a little bit about that, and hopefully at the end, I will try to tie it all together. So Norman Sutton once told me that if you're and those of you who have interacted with people at the DOE know that we talk about this old adage about a picture's worth 1,000 words. What he told me was the only way that you can get them to pay attention is to have a picture and then point to them and tell them how that manages your particular interest and theme. And so mine is sort of here. And that is that I've used a variety of neutron and X-ray sources, both high, I apologize if it gets wordy. We just finished the experiment at Haifa yesterday morning at 2 a.m. And driving, those of you who've been there, driving that dark road at night, well, there were no deer. But it was interesting. And my students say that I'm still young. NSLS2 exists now, but some of the work that we did were on a diffraction in a UV line. We do STM and AFM atmospherically. We make materials, and then we try to do simulations and synthesize the material that we look at. and I hope you'll get that sense. We have worked at a few of the joint institutes, both CNMS and the Joint Institute for Computational Sciences, but over time it's turned out that fast computers are cheap enough to buy that sole use it really tends to be something worthwhile. So, what did we want to do? We wanted to make materials and study them. And these days, nanoscience has kind of moved away. Now we talk about things like energy materials. Well, really we synthesize materials. And the materials that we have an eye on have to do with the fact that we're interested in things that might be photo or optically active, as well as chemically important for sensors or conversion. And I won't tell you about our recent banana sensor, et cetera, but if you're interested, we'll tell you about that. My thesis work was on ethylene binding to surfaces. We want to ultimately test folks that use molecular dynamics and density functional theories, because really, if you don't have experiments that put their feet to the fire, you don't really know whether the result is going to be correct. And in the old days, anybody can buy programs to do DFT, et cetera. The question is how accurate they are. And one of the ways to do that, if you've ever done thermodynamics, is to make sure that they're at least thermodynamically correct. And so we become thermodynamicists even though we didn't want to. I care, and so the mathematician in me cares about things like how does symmetry, I never took a course in organic chemistry, so all right, it's clearly not a chemist, but I do know how to read. But one of the things that if you are an organic chemist, is a super beauty about all of the different symmetric molecules that you can make. Bob has spent his time with things like C60 and other things, and it's that symmetry that I've been intrigued by. How do you take simple molecules as simple as methane? So most of you know that it's tetrahedral-like, but it has both a threefold and a twofold axis. And you can imagine that if you bring a molecule with different symmetries near exposed surfaces of different symmetries, that the physicochemical properties might be different. And so I've been intrigued by that. And I've also been intrigued by a different thing. And Bob reminds me of this. When I first came, I taught Gen Chem for 5 years. And one of the things that you try to get across to young folks is the following. You study homologous series, right? The last year was the year of the periodic table. It was chemists who actually started to look at those similarities. So I promised myself that what I would do when I was at UT was study a couple of homologous series. And so what we did was we took the linear alkanes, and now we're working on the cyclic alkanes. We're almost done. Now, where do you stop? Well, I stopped at 10, because I used to say that if the molecule had more than 5 atoms, I was in trouble. So you can see I progressed just a little. And the fact is how is it that both the surface and perhaps the tunnels, surfaces broadly defined, affect the physical chemical properties? And then finally, I want to combine those techniques and modeling, and I've worked with some really great people over the years to understand how it is that we might make new materials. And I hate the words big data, I hate the words artificial intelligence, so go tell everyone that I hate those. But the fact is what we really want is real intelligence, and we want to apply that in big data sets. That I appreciate. So, really? Yeah. So my daughter, who's a physicist, always says, Dad, you don't say in your lectures things like shit or hell. But I hope what you're saying to yourself is, what the hell good is this stuff? Because when you're talking to your grandma or your parents, whatever, and my dad was a jeweler, and he's an Italian guy. Hey, Jack, his son is a physicist. He gives him the physics of like X-lax. It's my dad's favorite. He's just turned 94 on the 7th. And I guess it takes a certain amount of, but the things like gas storage and separation and catalysis, you want to know something about catalysis, go talk to Steve. He spent most of his life learning about some really important things. But we talk about things like lubrication and corrosion. Those are really, really important phenomena. And people have talked about it for years. Am I not right, Steve? And the idea is they made some great advances, but they're tough problems. And surface wetting, well, if any of you have ever used Rain-X, then you know about surface wetting problem, because water beads up on your windshield. And so it has to do with the fact that people are now interested in things like lotus leaves, etc. But those are interesting problems. So why would he ever take neutrons to study these materials? Well, Bob touched on one of them. But this one is just as important. Sometimes what you want to do is use photons like lasers, etc., to stimulate chemistry. But I wasn't smart enough to do that. I told you I'd never studied organic chemistry. Oh well. But the fact is neutrons don't stimulate chemistry, at least at the energies that we're interested in. And so we're not nuclear chemists. The other thing is you can simultaneously probe both the structure and the dynamics over wavelengths that are important for things like the CH stretch, and those of you who study physical chemistry or did an IR experiment, etc. I just want to remind you of one thing. And it comes here where there's no selection rules. But the important part is when you thought, if you did a IR experiment, the fact is what you were really measuring was the change in the nuclear distance in things like a CH stretch, right? Or a CO stretch. And the fact is it's the nuclei that matter. You got to hope that the electrons follow along. Because if they don't, then of course it makes some particular studies difficult. And that is, symmetry is basically the root of the difference in the optical techniques as compared to the neutron one. In neutrons you see everything. You see the rotations, you see the vibrations, as well as the torsions. And that has a big advantage because you can simultaneously look at the structure. And you can look at the structure, say, of your catalyst support, the thing that you put your platinum or your rhodium or your iron or whatever on, as well as the catalyst itself and the reactants, and follow the products. So I just got to make sure. Okay. And they're penetrative. And so this is a 2 3/4 inch stainless steel flange with some catalyst trapped between the two. And so you can actually shoot your neutron beam through this and actually look at what happens. And you can do that with quartz tubes, etc. And that's a difficult thing to do with things like X-rays and other types of optical photons. You have to make sure you have the right window, for example, that doesn't absorb the IR if you're doing an IR experiment. So, maybe I'm just lazy. I'm trying to be self-deprecating because being a scientist is a privilege. The rest just happens to happen. But I think that if I had to sum up why it was that things have gone well for us from the fundamental studies and our own intellectual progress, it has to do with the fact that we've taken prototype systems that are simple, like rock salt structures, magnesium oxide, simple metallic systems, semi-metallic, like graphite and boron nitride, and use those to study surface interactions. We've gone to alumina and decorated alumina these days, but they all have a little bit of messy problem. Alumina has a whole bunch of phases, and any of you who have ever worked, for example, with, it's called Arconics now, not Alcoa, but the fact is that these transition aluminas are really cool, but you warm them up a little bit, the surface changes, the structure changes, and really, when you deposit a catalyst on them, it changes even more. And looking at how the catalyst, as well as the catalytic agent, the support, and the metal change, can cause real havoc. Am I telling the truth there, Steve? He spent a lot of his, they did some really elegant work, but the thing that drove us all crazy was what happened at the interface, both of the catalyst itself and the support. Because when they change, you have to have a way to track that. And what makes good catalysts and bad ones depends on that intimate balance. So we were lucky, and in fact, a dear colleague of mine, Walter Kunman, Walter is simply put a wizard. He's retired now, but Walter is the sole patent holder of the metal film resistor and the co-patent holder of the solid-state capacitor. So he worked for RCA before he went to MIT Lincoln Labs with the guy that just won the Nobel Prize, John Goodenough, and he made a lot of materials. Goodenough's the theorist, not an experimentalist. He made a lot of materials there before we stole him at Brookhaven, and I inherited him when I took over the chemistry group. We became great friends. And so the whole idea is we want to try to take these materials and either decorate them, dope them, or functionalize them in order to create these new materials with unusual properties. And I'll tell you a little bit about some of them. I apologize if I rush through, but I can give you the flavor and I can go as slow as you want, but I'm going to try to use 2 examples. So one of the examples that we've been able to do is look at and produce large quantities, because remember, neutrons are a bulk probe, so we have to produce mole quantities of these materials, and we want them to be uniform. And so we've been fortunate enough to figure out how, in fact, to generate things like these tetrapods of zinc oxide. And then we can deposit things on those, and whether they're tetrapods or rods or plates, they're stable enough for us to deposit either by solvent-based methods, or now what we're starting to do with physical vapor deposition methods, these particular metal catalysts on them. So this is one of the classic materials that we've been looking at now, and the other one is how I first started, and that's with magnesium oxide. We can produce these cubes from 5 nanometers all the way up to 500 nanometers selectively, so they're a very narrow range. And in fact, some of you might know that if you talk about the stoichiometry, in our case is 1 magnesium atom to 1 oxygen atom, you can dope in things like metals, and then you can have the general expression Mg 1 minus X R X O, and so we can put in things like copper or nickel or iron. And it stretches back to a problem actually that's been around for a long time, and that's this whole conversion of methane to methanol. And you need really good, well-characterized materials to do that. And so we've been lucky in the sense that they're all produced that way. We have a patent to do that. We almost burnt down the chemistry department when we first did this because we were oxidizing up liquid magnesium in a crucible and then vapor and training it. Magnesia crucibles don't handle things very well, and so we finally came along to the fact that we could use graphite particles, form an intermediate carbide, and then decompose it, where we could control not only the fact there was only magnesium vapor in the reactant flow, but also the size of the droplet. And that, monitoring the size of the droplet determined what the sizes of the particles would become. And I guess the apparatus looks like this, and it looks like a lighthouse when it's working because it's a high temperature process. And amazingly, it works well enough to give you really narrow selectivity. So we were happy about that. And sometimes being lucky is way better than smart. And so here's an example of how it is that this reaction begins. There's a halo. We can introduce gases here, and we can start off with metallic compounds that allow us to introduce another material as a dopant. So that's the way it goes. If you care, you can look up the patent, and it's the important thing is it was really fun learning how to do it. I told you that we started to learn how to deposit materials on surfaces, and here, thanks to the Z contrast hot atomic resolution STEMs at Oak Ridge, dear Angela Pini worked with us in actually starting to examine the behavior of palladium decorated zinc oxide. Now, I'll talk a little bit about this later, but it has to do with how it is that hydrogen many of you know that hydrogen, palladium sucks up hydrogen like crazy, and you know it was the roots of cold fusion. They had palladium electrodes, and then they cracked. And, well, the fact is palladium is a really, really interesting material to study hydrogen spillover with. And that's actually how Eastman came to me, because they held a patent on this particular material, but they had no clue as to how it is that it actually worked. And they spent a lot of time working on that, and that's all I can tell you. Go look at their patent. But it was really great, and they were great with us. But I want you to focus on this part right here. It turns out that these are false colors, but the Z contrast allows you to know that this is palladium and this is zinc. The interesting thing is the interface, actually, it's not because of the till. The interface zinc actually wets a little bit at the palladium surface. So there are some compounds that are formed here. And remember how I said that about the catalyst support interaction. It's really what goes on right here probably is a major part of the story. And we've started to work on that a bit with neutrons, and I'll show you the progress that we've made. And I'm hoping I'm keeping it, level okay. I can go up or down however you like. But the other thing, so those are solvent-based. We use palladium acetate to deposit those materials. Remember, it's the guy that only knows how to read but doesn't know any organic chemistry. But it turns out that using magnetron sputtering, etc., we've actually now started to learn how to deposit in a solvent-free like method copper on the interface. In the story, you can look it up. The patent, it turns out, for methane to methanol originally was zinc oxide decorated with copper by the Japanese. And then they had to introduce some nickel because it started to poison. But I wanted to get my hands on using things that we can make easily. So we decided actually to put some copper deposit on the surface. And the one thing I want you to notice is the highlighted things there, that turns out to be the copper. We've managed to be able to put copper substitutionally into the surface, only in the first two layers. Now it's not ordered. It actually turns out to be a little bit stochastic. And I don't remember whether I have another, I don't. The fact is, what you can actually see if you look at the normal position is that the copper actually is randomly distributed in that region. And so we're really excited to take a look at the chemical properties of this. This is a new experiment, and Matt Chisholm and Gert Duscher have been kind enough to let us sneak into places where we would normally have to pay to use them. That's a complaint, actually, that all scientists should have, that suddenly, you know, the national facilities somehow or other pay for play, which is crazy. Your tax dollar pays for those. I'm going to tell you a little bit about how we compare. I told you this symmetry relation. So we're going to take molecules of the same type and we're going to adsorb them on these surfaces. This is the square surface of magnesium oxide, so it's fourfold symmetric. And this is graphite with sixfold symmetry. Boron nitride has two chemical differences, but its structure is very similar to graphite, except for the fact that it's threefold symmetry at the exposure. And to give you some idea about that composition and interest in the two symmetries, for example, some of the things that we've looked at are things like cyclopentane. And now, so the cyclic molecules we're looking at now are cyclohexane, cyclopentane. We've just studied it high for cyclopropane. And so what's cool is that here you see that we have a threefold surface on some frustration, because how is it that it's going to organize? Now they might order next to each other, so there's a triangle up, triangle down, a triangle up, but our simulations don't quite show that, and I'll show you some of them in a minute. You can imagine now, so there's the ones, the fourfold or the twofold ones really like it here, but those that don't have those elements get frustrated. On this case, clearly the ones that have threefold and sixfold symmetry like it here, but the fourfold ones are going to be frustrated. So that's the simple basis of, you know, a guy that's not so bright in the way that they think about how we're putting Lincoln Logs together, if you'd like, or in fact Legos. And that's the mathematical key to doing these things. And so some of the cyclic molecules that we've now just about done all of the thermodynamics with are shown there. Let me just go back. Actually, it was a spectroscopy experiment that had me start on two. One was, you know, if you do study organic chemistry, one of the things that you learn about are the two configurations of cyclohexane, right? The boat and the chair. And so I thought, well, shit, I never took a course in organic chemistry, but I might as well, you know, tempt students into using some of their background. Most of the students that work with me are chemists. And I said, well, we could study that. And we have, and it turns out there's some great things, and I'll show you some molecular dynamic simulations of those. But the other one really was one, it turns out cyclopentane has a really interesting property. Think back to when you learned about benzene and, you know, the sort of snake chasing itself in terms of the electronic structure. Cyclopentane actually has pseudo-rotation. So what happens is the molecule kind of flexes in such a way that it looks like it's rotating. And Herb Strauss at Berkeley actually spent a lot of his early career, and I heard Herb give a talk in my really early days, in his younger days. He's quite old now, maybe dead, I don't know. But the spectroscopy is really hard to do. And so what I thought was, shit, if you bring it next to a surface, it'll freeze out some of the modes. And you could compare that to what happens in the sort of gas phase and start to sneak through. And we're making progress. It's actually one of those things where, you know, when it works, you tell everyone, and when it doesn't, you never studied that. You learn as much from things that don't work as they do. And you all know that because one way or another, technologically or scientifically, you get it. So these are the approaches that we use. We use thermodynamics, MD, molecular dynamics, and neutron scattering, and I'm going to zip through those because I still will stay. And tell me when you want me to stop. So the thermodynamics that we do, we use absorption thermodynamics and high-resolution volumetric absorption isotherms because we're trying to prepare these single-layer or multi-layer systems so that we go to the X-ray sources or the neutron sources and don't waste any time. So we're ready to go and we can deposit these things in situ, etc. I also was intrigued by the transition from 2 to 3 dimensions. How is it that things at the interface change in their thermodynamic properties to what they're like when they're a bulk hunk of methane or a bulk hunk of nitrogen and argon? And so a lot of this is I needed a way to study that. And here's a simple example. We're really lucky because methane absorbs on magnesium oxide in a layer by layer like fashion. And in fact, I looked back through some of the old notebooks. We actually can identify 6 and 7 layering transitions. And those are typically talked about as being wetting systems, systems that grow layer by layer like at the interface. What's cool that I've learned since then is these are solid layers, so what happens is you deposit the first layer, then you increase the chemical potential because this is at constant temperature. And if you take the logarithm of that pressure in your head, then it's basically mu, so there's the chemical potential. You need a higher chemical potential to condense the second layer. Needless to say, you need a little bit higher one for the third, etc. And there's some key systems that you can study that with. It turns out that says that they're the same thing for hydrogen. Hydrogen, actually, you can follow, in some cases, 7, 8, and 9 layers. These are the thermodynamic measurements that we make. And it's always funny when I was a young student, and a thesis student, if you measured one of these molecules, mine was ethylene, that was almost a thesis work. Turns out now we have automated machines that we've built and figured out the algorithms to compose one of these. It turns out that any one of these measurements takes about 3 or 4 days. It's all run, automatically. We have 10 of these machines that run that, and it allows us to start to do this. So one of the things that you'll notice that they're over temperature ranges that are interesting compared to their bulk triple point. You remember that that's the place where solid, liquid, and vapor coexist. So that's a good touchstone. And in fact, what you can do is you can take the derivatives of these individual layer transitions and see how they change as a function of temperature and as a function of composition of either the molecule or the surface. And you can learn things like it should say, it will, heats of absorption, the differential entropy, and if you care about this, you can read it in a number of publications. You can do what's called modified Clausius-Clapeyron. That just allows you to follow how it is that these thermodynamic quantities exist. Go to the Bureau of Standards and you can find this out from years ago for all of the variety of molecules, etc. But I like to show this slide for a different reason, and I hope you get a chuckle out of it. I remember sitting as a young guy at American Chemical Society, American Physical Society meetings where they were theorists, and they show this giant table of numbers that they calculate. I'd sit there, and I would sit about just behind the second layer, and they're like, I didn't wear glasses. They're like, what the heck? So it's sort of like this is turnabout is fair play. One of the things that's interesting is you can actually see in this case that the binding energy of, in this case, cyclopentane to graphite is the highest as compared to boron nitride as compared to magnesium oxide. And at some level, it's interesting because it's pseudo five-fold symmetric. It shouldn't like any of those systems. But when it's close to the 6-fold ones, it really kind of likes to sit there. So I've enlarged it here so you can see those just to... It allowed me to tell you the wisecrack. We do molecular dynamics simulations. And so one of the first things that every student in the group, I showed you that first slide, every student in the group when they leave has had to do some synthetic project, had to work in glove boxes. All of our materials are moisture and air sensitive. They have to do some calculations. They've had to do thermodynamics. They get to learn low temperature and vacuum techniques, etc. And those that go to industry, it's a reason why those last folks start out at 6-figure salaries. And I'm happy as punch for that. But one of the first things we do is just do a simple energy minimization calculation. We just calculate how it is that the molecule interacts with the surface. And we try to identify, we cover the whole surface by taking advantage of their symmetries. So we break them up a little bit and then just reorient the molecule, run energy minimization calculation. All that says is we look at all the different configurations and we sort out the lowest one, and then we take a look at those. And so here, for example, cyclopropane, which we just studied, you can see that it really likes to sit on graphene and boron nitride. And it can either choose to sit, in this case, a top boron or a top nitrogen. And so, and really those simulations show that. You can notice that cyclobutane, it likes to find, regions where it fits in the crack. I should tell you, this is the only one that's not distorted. All of the other ones are slightly distorted. So they're not perfect squares or cubes, etc. We wanted to study cubane for the longest time, but it turns out that the dear chap that first invented that, he said, "You damn neutron scatters, you never send it back." And this is a guy at Chicago. And so he wouldn't send me in. It's a 22-step synthetic process. So one of the other things that we do is we study what happens when we increase the number of molecules in the cell. The reason why I've shown you this, the details aren't as important as the fact that molecular dynamics simulations basically follow Newton's laws of motion. So what you do is you start off with a particular temperature, you have some particular velocity, you know what the energy is because it's basically just K Boltzmann times the temperature, and then you follow that and follow the trajectories for some certain amount of time. We're really lucky because it turns out that we have 1 femtosecond step sizes, and we really can run them forever. Typically, these particular runs on fast machines are on the order of 3 or 4 hours apiece, and it's really not so bad. What we can find is things like what the individual structures are of these particular systems. And so one of the things that you can do is you can look at the low temperature configuration from these simulations, and then do things like determine what the crystal structure is. And I won't say radial distribution function unless, am I okay with that? So in other words, right, you pick some center, you move out, and you look to see where it is that the height, for example, the center of mass is. And those are the sorts of things we do. And this gives us a little key to when we do the neutron experiment, what are they going to look like? And I will make sure that I get to those. But there's an interesting phenomenon. I mean, those of you who may have had some interest in things like electrolytic cells and what happens at interfaces in those particular studies know about this electric double layer that occurs at the water sort of electrified interface. There's an increase in the density around those points. It turns out that depending on the interaction, so this turns out to be the concentration profile, in this case, of cycloheptane on a hexagonal boron nitride. We've done these simulations for all of the ones that we've studied, but this one is a good example. What this does is it just tells you the location perpendicular to the surface of some particular component of the molecule. It turns out you follow both the carbons and the hydrogens. And you'll notice that there's a bunch of temperatures that we've done these studies at, and you'll notice that as the temperature goes up, which is sort of this way, you'll notice that they get more and more distributed. And that's partially because the surface is starting to lose hold on those particular molecules. What's rather interesting is that we found that you can have layered liquids. So the molecules closest to the surface stay pretty well organized. Then the next layer, depending on what the temperature is, they start to translate, and then the one above that. But they tend to stay within their particular layers, although you'll see there's a little bit of interlayer traffic here. These are some equilibrium snapshots. But what's really interesting is whether you're at 5K or whether you're at 280K, the layer closest to the surface turns out to be stabilized. And in the cases where the molecule and the surface, where the surface has some grip, it turns out it raises the melting temperature. Typically the melting temperature of a single layer of atoms at the interface is about 70% of the bulk triple point. So they all tend to melt at a lower temperature than what they would in the bulk. In these cases, it turns out that the melting temperature of the layer near the surface extends above the bulk temperature by 20 or 30%. And it's mostly because the upper layers act like a piston. They're attracted to the surface enough that they keep the molecules in the interface organized. And my dear friend Stuart Clark and Tom Arnold, who did a postdoc with me, they measured some differential scanning calorimetry, and they actually saw this peak that they would see the bulk like melting, and then, depending on what the particular molecule was, they'd see this peak that they thought had something to do with the melting of the surface. When I was still at Brookhaven, we did this with argon and saw the same thing. Argon, it melts about 20% above the bulk triple point, the surface layer. And that had a lot of interesting science and caused a lot of head scratching and then finally some understanding, which is, again, a satisfying thing for science. So you can do these things, and I just said that it stabilizes this layer close to the surface. Well, what do these simulations look like? So cyclohexane on MgO is kind of cool because when it moves on the surface, remember, it has the fourfold symmetry. It kind of runs along like a wobbly tire. And if you watch it, it turns out the surface kind of wags and jiggles. If you put that on graphite, it turns out it hops over to another top of the hexagon, spends some time there, and then rapidly moves to another one. So there's some very differences in the dynamics, and that's one of the things we study with neutrons. And so here, if you watch this one, you'll notice that if you look really carefully, and you can look at it later if you care, you could trust me. The fact is it spends a lot of time, they'll spin around over the hollow sites of the hexagons, and the dynamics are very different. We've studied that. Okay, right now I'm just in the home stretch. So we did some nice work with, in fact, Bob Sumpner and a postdoc that we employed to look at this charge relocation. I told you about this. This is palladium decorated zinc oxide. So I'm back to that red and blue picture. And so this is what you can do with high quality electronic structure calculations. You'll notice that in fact there's a lot of charge distribution. That's what these globs are, if you like, of the electronic charge near the surface. That's very different. If you look at this behavior on graphite, it's really located around the metal palladium. So that's all you get for that. So here's the neutron part. Neutrons scatter from materials differently. And the real advantage is that they scatter from hydrogen and deuterium in a really special way. And so I tried to show you the comparison between the scattering, the absorption, and the incoherent scattering cross-section. And the one that you should really look at, this is spin incoherency, is hydrogen itself. And that's what makes it so attractive to do inelastic neutron scattering with. Okay? And that's kind of what matters. The rest is, you can read it if you like, but the idea is neutrons are really good to study hydrogen-containing material. One of the real hopes, and maybe Steve has heard me say this before or not, but one of the classic things that you do in classic surface science is look at the poisoning of certain catalysts with CO. Years ago, so my goal with building this instrument Vision was to be able to look at the CO stretch, and I can tell you now that it works, and it works pretty nicely on Vision, but that was something that neutrons could never do in the past, and so that was really the hope. This is the neutron scattering 101, only equations, I think. The important part is the experiments that we do turn out to be time of flight experiments. If it turns out that the incident energy and the final energy wave vectors are the same, then you get diffraction, and that's elastic scattering. But if it turns out that you transfer some energy either to the sample or the sample to you, then you do inelastic scattering. So you can measure those things, and those of you who have done Raman know that you can talk about the Stokes and anti-Stokes lines. Well, in this case, it turns out it's either neutron energy loss or gain, and you can also follow how it is that the neutrons randomly lose some energy. And that quasi-elastic scattering allows you to follow things like rotational and translational diffusion. Okay, and so we've done those things. How many of you have ever done an X-ray diffraction experiment? A few of you? That's perfect because we need some experts in the audience. So this is the diffraction experiment with neutrons from a graphite sample. It's vermicular graphite. It's crystalline. And you'll notice that why it is that I do what I do is because if you absorb something like a single layer of acetylene on the surface, then you can see the big difference between the two. And that's shown here. So now you know why it was that tenure happened at Brookhaven, et cetera, right? Oh, wait a minute, maybe I should take the difference between the two of those. So there are two things that you should see there. One of them is that you notice that there is a difference. The other one is that the shape of this particular diffraction pattern is not symmetric. And that's because this is only a single layer of atoms, and in fact, you only have two Bragg conditions that you have to satisfy. So only the projection of your rod in reciprocal space, because there's a bunch of rods, only the projection on the scattering plane has to satisfy what's called Bragg's law. Now I know that's a lot of words and that's tough, but you should notice that it looks like sawtooth curves. And that calculation is one that we've done years ago. The other interesting thing is that there's a strong quadrupole moment for acetylene, and so even though it sits on that six-fold graphite surface, it forms a square T. And that fit actually tells you that it's a square T and they're separated by about 4.5 angstroms, the lattice. That's not the only thing that we did, and now I'm going to run through them quickly because there are a bunch of examples. This turns out to be butane sitting on a magnesium oxide surface, and we know a lot about that. This is really crystallography in 2 dimensions, and it's pretty tough actually to do. I'd be lying if I didn't say this is one of the best structural analysis that we ever did, although now at HIFER we actually might, given a little bit more time, start to change that. And so it turns out this is how it is that butane, a single layer, orients on the surface.
Right. Thank you.
But if that one's not good enough, you can... So here it is how hydrogen sits on the surface. Again, these are single layers, and they're different densities. And so the lowest, it turns out that at low densities, it turns out that it has this what's called centered 2x2. So it doesn't sit on every lattice site. It sits on every other lattice site, and there's one molecule in the middle. So that's the nomenclature. But actually, as you increase the number of molecules in your cell, the chemical potential, it actually forms a hexagonal phase. And that hexagonal phase is actually more dense than any of the bulk phases, stabilized by this interaction with the surface. You can do these measurements either as a function of density. Put more and more molecules in, it turns out that the structure changes. And it's really beautiful, and for experts, it turns out that it's what's called the devil's staircase. And so that 2x2 gets crushed in one dimension. So it starts off as 2x2, then it goes 2x4, then it goes 2x6, and then the symmetry in the structure is such that it then becomes hexagonal. And so that was just a lot of fun, and we know where it is that the hydrogen sits, and those are... But the last thing that I'm going to do is tell you just a little bit about... Have all of you studied physical chemistry or physics as an undergraduate? Do you remember the first dinuclear system that you looked at? Be brave. You want to say H2, but it really wasn't. It was H2 plus, because that was the single electron one, all right? And the reason why I tell you that is because H2 plus, and Bob knows this as well as others, turns out that H2 plus, if you look at the internuclear distance, it's about 20 to 25% further apart, because only the one electron doesn't screen the proton in the other nucleus as much, so they push apart electrostatically, right? You throw the other electron in and they move together. So I need to have you keep that in mind. Anyway, this is the ortho to pair transition. It's a rotational transition that you can measure for hydrogen on magnesium oxide, hydrogen on graphite. This is basically where it is that the bulk ortho to pair transition shows up. If you're a chemist, you like 120 wave numbers about. If you're a physicist, you like about 50 millielectron volts. You choose. But when you put it on magnesium oxide, it turns out actually that the molecule actually is hindered a little bit, and so it reorients a little bit slower. We know that this is a rotation because if we substitute H for D, and there's where you pay a big price in the scattering cross-section, it moves down by the ratio of what's called the reduced mass, right? It gets a little bit heavier, so the moment of inertia is a little larger, and so it slows down. And you see that. Keep that in mind. So this experiment right here at ISIS spallation source took 2 days to measure. I almost got shot. But the interesting thing is it's not 2B. It's not B either, but That's the question. We've done these things at a variety of different systems. It turns out that we can study those as a function of the density. And I just want you to show you that, in fact, you can start to get some behavior in the other layers. And I'm going to rush through that because the question is how do we change? So now I'm going to go back to that palladium zinc oxide problem. So here's what the ortho to pair transition looks like there. It turns out that it's not at near 14 millielectron volts. It turns out to be at 6.45 millielectron volts. And it turns out that when you have a single axis rotation, the ortho to pair transition, both in graphite and the gas phase, etc., is symmetric. All right? But in this case, it looks like a merry-go-round. And that means it's the difference between the two transition levels isn't 2b, it's just b, the rotational constant. I asked you about that first diatomic for the following reason. You remember when ice skating, figure skating used to be a part of the Olympics and everyone paid attention to it, etc.? Remember what the skaters do when they do that spiral, right? What do? When they want to speed up, they take their hands and they move them close together, right? When you want to slow down, you do the opposite because you change the moment of inertia. In this case, it turns out that the hydrogen that's absorbed on this palladium, it turns out the actual bond length increases. And it in fact slows down. And that's what happened when we've done these molecular dynamics simulations. I'll show you them just because there's the calculation that we did with Bobby and Lalo. And in fact, we actually know what's going on. I just want to show you that because I'm going to stay as close as I can to that. We studied hydrogen spillover. So that's what happens when you bring hydrogen in and interact it with a catalyst. And what happens, and I knew nothing about this when I first started, it turns out that the hydrogen becomes active and it moves along the surface and then reacts with some other molecule or some other site. And neutrons are good for that because I told you could do things like quasi-elastic scattering. This is that quasi-elastic scattering. And as you increase the temperature, it turns out the molecules are more and more both rotationally and translationally moving. And this is, if you can follow that plot, and you notice that right around 35 to 37 degrees, they actually start to translate. And they're complicated calculations. The interesting thing is what happens on the surface. We've measured actually the fact that the hydrogen actually interacts with the zinc oxide palladium decorated surface. And here's two of the inelastic neutron scattering spectra, one for the OH WAG and the other one for the OH stretch. And years ago, you'd never be able to do this with neutrons. That's the bottom line. How did we do it? It turns out that actually was done at ISIS. But it's a good example. Or no, maybe it was done at Los Alamos. This is vision, and I just remind you that Humphrey Davies said that, you can, if you do a nice instrument, maybe you can do some good science. If you're interested, you can read what happened. They're not small instruments, right? I mean, these are big time instruments, so, roughly 50 feet long, and there's a, traditional person there, and so it's several people tall, and if you want to read about it, you can go and see what it looks like. But it's a serious spectrometer. It can do both diffraction, inelastic scattering, and what's called pair distribution function analysis. And it turned out to have the best pair distribution function analysis in the world. Here's the comments. It's 500 times higher throughput than the best instrument in the world. It's actually 1,000 times better, but it turns out that if you don't want to have what's called frame overlap, the fast neutrons from the next pulse catch up with the slow neutrons from the other pulse, you have to operate at 30 hertz, unlike the 60 hertz at the SNS. So for certain experiments, it's 1,000 times faster. There's computational tools. The interesting part is right here. You can actually do a little bit of neutron gain, so you can do that quasi-elastic scattering actually on vision, and you can go all the way up to 7,000 wave numbers. I'll put some perspective on that. The HH stretch is around 4,000 wave numbers. People at meetings, and it's embarrassing, so you crawl under the table, but people have described vision as a game changer, and it's probably one of the best instruments at the SNS right now, maybe one of the top 2 or 3. Here's that same experiment that I showed you before with the ortho to pair conversion. The other one was done at ISIS. This was done at Vision at the SNS. So there we go. There's the, these are all with pair hydrogen on graphite. This turns out to be HD on graphite. Remember how long I said that it took in the past, so let's make a comparison. This spectrum for H2 took 5 minutes at Vision, and the HD one took 30 minutes as compared to 3 days. So I think we've made some steps forward. So without killing you, I hope that I've convinced you that you can use thermodynamics, simulation, synthesis, etc., to learn something about surface phases and a whole variety of them. We are trying to develop energy materials, but anyone who's truthful about that knows that it takes time, and maybe we're slow. And then the encouragement always is for people, maybe you can take your the work that you do in your laboratory and actually use the national labs as a part of your research. And with that, I apologize for being a little long, and thanks you for your attention.
I think we have time for a few questions.
Well, you must have some idea of what these new energy materials would be. You just sort of left us hanging. What?
I did. So it turns out that both a fellow who is now dead, but was part of the whole surface science entourage, spent the last part of his career at so it's what do you call it, station in Texas, and that's dear Mr. Goodman, right? It turns out that Wayne Goodman, yeah, he sadly is dead. He and a colleague of his spent a lot of time trying to identify the fact that, for example, magnesium oxide would be a good support for doing methane to methanol conversion. And one of the problems that you have is when you're trying to deposit a catalyst on a support, when you do it in a solvent-based way, a lot of times what happens is you deposit a lot of shit along the same time. And you can heat it up, but then what happens is you change the habitat of the catalyst itself, the metal. One of the things that we found now, and that's the stabilization with the copper on the MgO, etc. They're really in the surface. They're not little. We've actually deposited single atoms too, and MgO it's really flat, but there are some steps on there because the equilibrium surface is 100. We're really excited about the initial results that we have in terms of things like methanol production. But my thesis advisor always said, making a claim before you know that you're right is kind of a fool's game. If you're right, you'll be okay. And the other one is what I didn't talk about was the hydrogen spillover. The hydrogen spillover on a palladium zinc oxide, it takes place at about 50 Kelvin. When we first did that, I thought, shit, there's something wrong here, right? It's partially because we used normal hydrogen, not the para. And when you look at that, it turns out that normal hydrogen in the bottle is a combination of ortho and para. And it's the fact that it's in the slightly higher rotational state that actually makes it more reactive. So we went back. There's an interesting now recent study of looking at isotopically substituted methanes at interfaces, and the reactivity is different. And normally you say, oh, you put deuterium in, the chemical properties are the same. And so there's some thoughts that we're going to creep back to this whole one. But so that's the one I can tell you about. It's kind of like the sensor that we've made with ethylene. We filed for the preliminary patent, and I got my PhD in I have to think about it, 82. It's been rolling around upstairs for like 30 years. And it works really nicely as a detector. So the energy materials, we've done some gas separation things, but it's maybe it's nonplussed to say that the application was never really why I was interested in science. With the students, it's better. We encourage them to do that. They've gotten along, but for me, I'm going to try to remain as true.
It seems to me that this sort of thing, petrochemical industry would be very interesting because you could really design catalysts that do specific kinds of chemical reactions. In fact, I guess I was kind of surprised not to see more support, from big chemical companies on this.
I can speak to that. The problem always is that most of you have worked somehow or other or been related to Oak Ridge, right? When you work with at Brookhaven, that didn't happen actually. We only worked with BES. That was it. We didn't take money from NSF. I mean, I wrote my first NSF grant when I was pretty old. It was when I came here. So the fact is that when you work in some of the work that I can't talk to you about from Eastman, I mean, we've done some work with them recently, et cetera, you can't publish it, right? And until it gets patented, you can't talk about it. And at some level, that's a little unfair to students, right? Because everyone wants to know, oh, well, what did you publish? And I always say, look, have them call me and we'll talk about that. And it's worked. So there are there's a renewed interest now by the oil companies, if you like, for different reasons, for things like fracking, et cetera. And they're looking at how gases move through clays and things. And we have an expertise in that area. But it's only one person, right? I mean, people like solar cells and there's just I guess I'm a fundamental scientist, and that may sound like a crappy answer. But.
Well, I remember taking chemical engineering. I took a course in catalysis. And, I mean, there wasn't even any discussion of anything down at the atomic molecular level. I was trying to come up with models that are based on catalyst geometry, and this is all kind of revolutionary in a way.
Well, I mean, at Brookhaven, we received money from Shell, but it was, I mean, they just gave us the money, and they would come in and we would help them measure some stuff if we could and talk about it, right? But I think that most of the time it really was, it was corporate people working on those topics.
Okay, any other questions? If not, thank you very much.
I don't have any other answer. I'm not using it.